Okay, so in this video, we're going to move on to the encoder and kind of the menu that I talked about in the last video. So I've hooked up the encoder. So here it is, as I showed in the last video. And just to explain the pins on the encoder, these two pins here are the actual rotary encoder pins themselves. Typically this pin and this pin are attached to the interrupt pins on the Wattmeter 328, and then there's some code which I'll show that actually decodes the direction from using that. So the center pin is ground, and then the other side is the push pin, the push switch on the encoder itself. So you can see you can push the encoder down, and that activates these two here. Now note that the ground is tied together, so here's the ground for the push switch, and that is tied together with this ground here, and then these pins all go off to the board. Now note there's no, these just go straight to the pins on the Wattmeter 328, so basically you have to have input pull-up on there. Sorry about my dogs there. You have to have input pull-up on the pins themselves, otherwise they won't be read properly. So I got the encoder code itself from the, well, let me just demo the encoder itself. So you can see there, I've just got a little counter going, and that counter is updated by the encoder itself. So as I turn it counterclockwise, the counter goes up, and as I turn it clockwise, the counter goes down. And obviously, if I swap the pins over on this, it'll reverse direction. So that's the encoder working. Now onto the code itself, and as I mentioned in the last video, I did confirm I got the code from this from Instructables, so I'll include a link below to that code itself. But so let's just scroll up to the setup of the pins themselves. So I've got this duplicated here. I was just doing some debugging, but anyway, you don't have to do this twice. But basically, pin A and pin B are the two interrupt pins that I mentioned, and that's go up to the declaration here is pins 2 and 3 on the Arduino, which are actually pins 4 and 5, strangely enough. So they're digital pins 2 and 3. So anyway, you declare these pins as both input pull-up. You have to do that or it won't work. And then you have two interrupts to use on an Wattmeter 328. You attach the 0 interrupt to pin A, the 1 interrupt to pin B, and you make sure that this is rising, so it will be triggered on the rising edge. And so that's the setup of the pins, and then the code itself is it's kind of a little indecipherable, but I'll provide the link to the Instructables video. He does a great job of explaining how this code actually works. There's a little internal state machine in there, and basically the two signals from pins A and B are actually in quadrature, so it's able to detect the rotation by using the fact that those two signals are in quadrature. Now, as I mentioned before, the Wattmeter 328 only has 2 interrupts, so if you wanted to include multiple encoders on there, that would be certainly a challenge. But I only need one in this particular circuit, so basically that's it. Now, one of the things you have to watch out for in any interrupt processing, at least on an Wattmeter, is you can't do anything complicated inside the interrupt loops themselves. So both of these functions actually get triggered on a value change. So you can't update an LCD, you can't display something you don't want to write to the serial port. You want to keep that code as slim as possible. And then if you have a look in, so basically this change display function is invoked with either a minus or a plus, depending on the state in here. But I don't actually update the LCD in that. I update the LCD in the primary loop. So that keeps the LCD writing code outside of the interrupt processing, which is something you need to do. So anyway, I just thought I'd do this quick update on the encoder. So the encoder is actually working, and I can move on to the menuing next. So the Wattmeter is pretty much complete, or at least as complete as I'm gonna take it. So let me just walk through a few of the measurement readings from it. So I've currently got it at minus 45 dBm on the signal generator, and as you can see, some changes on the screen. I've now got it displaying both the value in dBm over to the right here, as well as the value in watts here, which is 32.1 nanowatts. So I've got a dBm to watts conversion calculator here, so let me just put in minus 45 dBm and see how close we are. And the answer it comes up with is 3.16 times 10 to the minus 8 watts, which is 31.6 nanowatts. So a little bit out there, but let's keep moving around. So let's go to minus 35 dBm. So minus 35 dBm, let me put that into the dBm to watts calculator I've got here. And that is 3.16 times 10 to the minus 7 watts. And you can see, so that would be 316 nanowatts, and the Wattmeter is showing 307. Let's do a different number. Let's say minus 28 dBm. And let me change that on the signal generator, minus 28 dBm. And you can see there it's displaying 1.5 microwatts, and the actual conversion is 1.58 microwatts. So let's just try one more number. So let's try minus 12 dBm. Minus 12 dBm is displaying 63.1 microwatts. And on the dBm to watts calculator, that is 63.09 watts. So you can see there's a reasonable level of accuracy there. And it does highlight one of the challenges with this is really there isn't quite enough resolution in the inbuilt analog to digital converters in the Arduino. And I'll talk about that a bit later. The next thing I want to show, though, is kind of the menuing system that I've actually got. So that's coming up next. So one of the things that I wanted to do is to create a simple calibration menu so I could control the mapping between the analog pin inputs to the Arduino and the actual power displayed. So in order to do that, I've built a simple menuing system here. That's accessed by pushing down on the encoder here, and you can see that I've got five different menu items. I've got the input attenuation, which I'll talk about in a bit later, but then I've got the slope and y-intercept for the forward voltage, and the slope and y-intercept for the reflected voltage. So actually, I can actually go in and change these values. So let me do that. So let's go to, let's say the slope currently is 0.195 for the forward voltage. To edit that, I press this button here, the edit button, and by pressing it, it moves to the different values. So let's change that to a 2 here, and then click through. Now that's saved 0.295 instead of 0.195 as the slope for the forward voltage. So if we go back, now we can see there's a very different value. Excuse me for bumping that. There's a very different value for the dBm here. So let's go back and change that to change it back to the original value. I just go in again, push, 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 change it back down to 1. Exit out, and there we are, back to where we started. So that calibration menu allows to change the mapping from the analog pin values to the dBm. It kind of allows that sort of inbuilt calibration. The other thing that I have in the menu is this input attenuation, and what this allows to do is if you insert, so as you can see, I currently don't have this with the directional coupler or with any other input attenuation. So the effective input attenuation is 0. If I were to put that directional coupler in there as specified in the original document, that has an input attenuation of 30 dBs. I'd put 30 dBs as a correction factor in here. So that's the simple menuing system that I've built in there, and I've included all that in the GitHub repo that I've created for this, so you can see all that code for yourself. So as I said, I'm pretty much done with a wattmeter at this stage. I'm just sort of this is a flyby of the actual install itself, just so you can see all the components installed. There's the LCD and the encoder and the edit switch installed in the front panel there. You can see at the back I've got the 8307 board installed on the back there. I have the main board mounted on standoffs here, but they're not currently screwed down. So that's pretty much it for the moment. What's next? I mean, there's so many. I mean, this is obviously a very simple wattmeter at the moment, but there's so many other things that could be done, and I might do those in some follow-up videos. But I mean, obviously one of the main challenges is the resolution of the Arduino analog pins, and you know, one of the things that we can do about that is I've already got a couple of these guys on order. This is effectively an external 16-bit ADC, and this allows for, instead of just 10 bits of resolution, 16 bits of resolution on the input. It also has an inbuilt reference voltage as well, so you don't have to worry about having your own reference voltage. And then finally, you've got programmable gain, and you can use the programmable gain to get a lot greater resolution within specific bands of the power output. So that would be one thing I wouldn't mind doing. Also, the power that I'm displaying is it's a simple instantaneous power. I don't have any peak or average that the original author had, so that's something I could do. Obviously, if I get forward and reflected voltage, I can display SWR on there, so I could use the menuing system to have different wattmeter displays. And then finally is the directional coupler itself, and I showed the directional coupler from before, and definitely that's something I could rebuild to do as well. So lots of different places that I could go with this, but as I said, this is probably a wrap for now on this particular project, and I will probably at some point in the future pick this up again and do some of those changes that I talked about. But anyway, I hope you all enjoyed this series of videos, and that's a wrap for now.